In this video, we'll talk about using algebra to evaluate limits, particularly in the case that the denominator of a function is 0. So just as a reminder, definition, if f of x is a function and c is a constant, we say that the limit of f of x is L as x approaches c if as x gets arbitrarily close to c but not necessarily equal to c, then the output of f of x gets arbitrarily close to L, and our notation for that is limit as x approaches c of f of x is equal to L. Okay, so we've seen that one situation in which a limit might not exist at a point x equal to c is when the denominator of the function is equal to 0 at x equals c. The simplest example of that would just be the function f of x equals 1 over x. And we know that in that situation, our function looks kind of like this. The function is approaching positive infinity from the right and negative infinity from the left. And that limit, the limit as x approaches 0 of 1 over x, does not exist. So there's a pretty clear example to see the kind of thing that we're avoiding. We're avoiding vertical asymptotes, either situations where both sides go to positive infinity, both sides go to negative infinity, or one side goes to positive and one side goes to negative. So there are some situations where even though the value of the denominator at x equals c is equal to 0, the limit of the function may still exist. Here is one such example. So we could observe that if we plug in our value c equals -1, the place that we're wondering about with the limit, into this function, well, we would have a denominator of 0 because we'd have -1 plus 1, and that's 0. But there's some hope because when we plug in -1 to the numerator, we also get -1 squared plus 3 times -1, so -3 plus 2. And so that's +1 plus 2, 3 minus 3, that's also 0. So that's a situation where we might just have a hole as opposed to an asymptote in the function. So let's see how this works. Let's look at the limit as x approaches -1 of this function, x squared plus 3x plus 2 over x plus 1. And we're going to see if there's any place where we could possibly, simplify this function. So one thing we could check is, can we factor the numerator? Can we factor x squared plus 3x plus 2? So let's see if that has a nice factorization. If it does, then what would we need? Well, the first term is x squared, so the first term of each factor would be x. The second is the last term is a 2, so we could either have a +2 and a +1, or a -2 and a -1. But we see that the middle term is a +3, so that tells us that this is going to be a plus and a plus. And we can verify, when we multiply the firsts, we're going to get x squared. When we multiply the outers and the inners, we'll get x plus 2x, which will be 3x. And when we multiply the lasts, we're going to get 2 times 1, which is 2. So great, yes, that is the factorization of the numerator. And so we've got, this is equal to the limit as x approaches -1 of the factored form, x plus 2 times x plus 1 divided by x plus 1. One thing to note here, do be careful about your notation. So do keep writing equal signs if things are equal. Do keep writing the limit as x approaches -1. So this is still equal to the limit as x approaches -1 of that whole quantity. Okay, so continuing on, now this is equal to the limit as x approaches -1 of canceling out the x plus 1 in the numerator and the denominator. So this is equal to the limit as x goes to negative 1 of just x plus 2. Why is that the case? One thing I'd like to highlight for you is that it's really important that this limit is here. So why is that important? It's important because in general, the function x plus 2 times x plus 1 over x plus 1 is not equal to x plus 2 at x equals negative 1. Because at x equals negative 1, this would be 0 over 0, which is indeterminate. So it's not equal to that at all points, but for x not equal to negative 1, then we're not dividing by 0, and this is an acceptable statement. So for x not equal to negative 1, x plus 2 times x plus 1 over x plus 1 is equal to x plus 2 because we're not dividing by 0. So remember that in the definition of the limit is for values close to c, for values close to negative 1, but not equal to negative 1. So values close to c, values approaching c, but not necessarily at c. And now this is just the limit of a very simple polynomial, x plus 2. And so at this point, we can just plug in. So we can just plug in our value, and we'd get x equals negative 1, so negative 1 plus 2. And negative 1 plus 2, that's easy to evaluate. That is just 1. So the limit as x approaches negative 1 of this function is 1. And if we graphed this function, if we graphed the function f of x equals x squared plus 3x plus 2 over x plus 1, we would find that this behaved exactly the same as the function f of x or g of x equals x plus 2. So x plus 2, 1, 2, that's a linear function so it's a linear function with a slope of 1 and a y-intercept of 2. It would behave exactly the same way except at the point negative 1. So at the point negative 1, there would be a hole, and that hole would be a what we call a removable discontinuity or a point discontinuity at the point x equals negative 1. So it would behave almost like the function g of x equals x plus 2, except at this removable discontinuity, except at x equals negative 1. So as x approaches negative 1 from both the right side and the left side, the function value does approach a value of 1. The function value just is not equal to 1 at that point. F of negative 1 is undefined or does not exist. Now here are a few examples for you to try. So find the following limits if they exist. As you're doing these problems, I'd like you to get out a piece of paper, don't try to do them in your head, and make sure that you are using good notation. Using good notation, one of the biggest things to be careful of is that you should only use equal sign when the things on each side are actually equal. So when quantities are actually equal. So one example would be, say, if you write that the limit as x goes to negative 1 of x plus 2 times x plus 1 over x plus 1 is equal to x plus 2, that is false. The limit over here, this limit as we saw, ended up being equal to 1 in the end. This is a function. So this is a function, this is a constant. Those two things are not equal. So make sure that you're writing limit as x approaches -1 every time until you actually take the limit. And when you actually plug in the limit as x goes to -1 in our example above of x plus 2, now that is actually equal to -1 plus 2. That is actually equal to +1. And notice that the limit is gone at this point. There's no longer a limit because we have taken the limit. We've plugged in x going towards -1 because it's just a polynomial and we can just plug in. So now we can use equals without the limit, and in fact we should not include the limit because we've already taken it. One last thing to note is just here, this is the limit as x goes to e. So e is a number kind of like pi. E is close to 2.718 ... It's a special number. We'll see later in the course some of the reasons why it's such a special number. So pause for a moment and try those on your own, and we'll talk about them in just a minute. Okay, so our first example, the limit as x approaches -3 of x squared plus x minus 6 over x squared plus 9. So the first thing we could do is just observe or check that when we plug in the value as x is approaching, if we plug in x equals -3 into that function, then our numerator is going to be -3 squared plus -3 minus 6 divided by -3 squared minus 9. So this is -3 squared is +9 minus 9, that is a 0. And if we look at the top, that's 9 minus 3 minus 6, that's also a 0. So this is undefined. So we do, in fact, need to actually plug in, or we need to do some algebra as opposed to just plugging in the limits. And so now we'd say to ourselves, okay, can we factor, in this case, we might need to factor both the numerator and the denominator for this function. So factoring. Let's first look at the numerator. So let's look at x squared plus x minus 6 divided by, we're just worrying about the numerator, so we're factoring that. So if this can factor, that would, or if it can factor nicely, it would be x plus or minus something times x plus or minus something to get the first term. And the last term is a -6. So that could be a 2 and a 3. One would have to be positive, one would have to be negative. Or it could be a 1 and a 6. And again, one of those would have to be positive, one of those would have to be negative for it to be a -6 in the end. But now we can look at the middle term, and the middle term is a positive 1x. So the single x terms need to add up to be a positive 1x, and that tells us that we're going to look at this situation as opposed to that situation, because that would give us either a -5 or a positive 5. So we're in this situation, and we want it to be a positive x, so that means that the 3 is going to be positive and the 2 is going to be negative, so that the x terms add up to be a positive x. So that's our factorization of the numerator. Good, we've got factorization there. You can double check by multiplying out if you wish. And we also want to factor the denominator. So the denominator, x squared minus 9. This is of the form of a difference of squares. And anytime that you've got a difference of squares, if you've got x squared minus a squared, that will always factor as x plus a times x minus a. Why is that? That's because we've got the firsts will multiply to give us x squareds. The outers and the inners will give us negative x or negative ax plus ax. And the lasts will give us a negative a squared. And we see that the the two middle terms cancel each other out. So this is 0, and this is x squared minus a squared. Okay, great. So anytime we've got a difference of squares, as in this case, this is the same thing as x squared minus 3 squared. That is going to factor into x minus 3 times x plus 3. Okay, so we've now factored both the numerator and the denominator. So now we can try to rewrite our expression involving limits. This is equal to the limit as x approaches negative 3 of the factored numerator, x plus 3 times x minus 2, divided by the factored denominator, x plus 3 times x minus 3. And now we can see, do these terms have anything in common? And in fact, they do. They've got this x plus 3 in common. Can we cancel it out? Well, yes, we can cancel out because this is the limit as x approaches negative 3. We're specifically looking at places where x is not equal to negative 3. So x is not equal to negative 3 because we're looking at values of x that are close to negative 3 but not equal to negative 3. So this is equal to the limit as x approaches negative 3 of simply x minus 2 divided by x minus 3. Now we've got a rational function, a polynomial over a polynomial, where the denominator is not 0 at the point x equals negative 3. So now we can just plug in the limit. And plugging in the limit will give us negative 3 minus 2 divided by negative 3 minus 3. And so that's negative 5 over negative 6, or that simplifies to a positive 5/6. Okay, let's look at our second example. Our second example, the limit as x approaches e of x cubed minus 1 over x squared plus 2. So before we get started, we above checked to see if we had a 0 over 0 situation. Here, let's just think about the denominator. So that would be x squared plus 2 at x equals e. So that would be e squared plus 2. And could that be equal to 0? The answer is no, because this is a positive value. E squared is positive, whatever e is. We happen to know e is 2.718 ... So this is going to be very far away from being 0. But no, e squared plus 2 is strictly larger than 0. And so we actually don't need to do our special algebra. We know that if we've got the limit of a rational function, of a polynomial divided by a polynomial, and the denominator is not equal to 0 for some open interval containing our point C, then we can just simply plug in. We can just plug in x equals e. We can just plug in that value, and so we're going to have e cubed minus 1 divided by e squared plus 2. And we could just leave our answer as that. That is a precise answer, e cubed minus 1 over e squared plus 2. That is a number. If you wanted to, you could also plug that into your calculator, and if you did, you would get 2.033 ... as an approximation. Okay, last example. So we are going to first just observe that, yes, the denominator is equal to 0 at this point that we're approaching. Denominator is t plus 1, which is equal to 0 when t equals negative 1. So we do need algebra to help us with evaluating this limit. The denominator is already factored, so let's try to factor the numerator. Let's try to factor 2t squared minus t minus 3. Let's try to factor that. So if we factor this, it's going to be the first term, 2t squared. Well, that would probably factor into a 2t and a t. That would be sort of the simplest way to get 2t squared. And the last term, the negative 3, well, probably this is going to be a plus 3 and a negative 3. We just have to figure out what goes where. So one of these is going to be a plus 3 or a negative 3. One of these is going to be a plus 1 or a negative 1. And we have to do a little bit of playing around to figure out which is which. So if we multiplied 2t by 3, that would give us 6t, which is going to be too large because we want just the difference of our terms to be negative t. So that tells me that I want my 2t to be multiplied by either a positive 1 or a negative 1, and therefore this term is going to be a 3. Now I want, again, these two terms to add together to give me a negative t. So I want my 3 to be negative and my 1 to be positive, because then my middle terms would be 2t plus 1, 2t times 1, 2t minus 3t gives us a negative t. Okay, so that means our middle terms check out. Our first terms multiply to give us 2t squared, and our last terms multiply to give us negative 3. So great, that is the factorization of the numerator. So now let's go with our limits. This is the limit as t approaches negative 1 of 2t minus 3 times t plus 1 divided by t plus 1. And this is equal to the limit as t approaches negative 1 of, in general, 2t minus 3 over times t plus 1 divided by t plus 1 is not equal to just plain old 2t minus 3 when t equals negative 1, because that would be a 0 divided by 0, or a 0 in the denominator, which is not acceptable. But again, this limit as t approaches negative 1, t is not actually equal to negative 1, it's just close to negative 1. So this is equal to this quantity limit as t approaches negative 1 of that expression is equal to the simplified version 2t minus 3. And now this is just, again, the limit as t approaches negative 1 of a polynomial or a linear function. And so this gives us 2 times negative 1 minus 3. This gives us a limit of negative 5.